Welcome to another session. Today we're going to look at Cocoon tools in Grasshopper. So we're going to do a little bit of mesh modeling. It's actually called volumetric modeling. And you can download this plugin from Bespoke Geometry. And this tool basically allows you to calculate the boundary of a field using Martian cubes. So you can input points, curves, and it can turn any type of geometric information into a volume. And we're going to do something cool with this tool using point and curve charges today. And this is actually what we're going to prepare today. And I want to experiment with kind of a volume that splits slabs, let's say, of a tower or of a building, using this sort of boundary condition, right? So we can think about this kind of a structural, maybe formwork, maybe concrete, and then we are going to divide the surfaces, divide the volume slabs into two regions with voids and floors. So I'm going to actually walk you through how this is made. We're going to do a little bit of look into how we can input point charges and curve charges, and then maybe extend this to a tower as well. So let's begin. I'm going to hide this, and we're going to start with a new script. And let's actually enable our grid. Okay, so I'm going to start with a volume that we're going to use for the population of the points and the curves. So we're going to do a box essentially. So I'm going to do we can do domain box or center box. A domain box is defined by a plane and size domain, so you can use the XY plane for the orientation, and X and Y and Z we can define them as intervals. So you can construct domains here. And we can define, let's say the center is located in the middle, and we can define kind of an interval, let's say minus 15 to 15. So if we start with, if you want to make it symmetrical, you can also multiply some positive value, let's say up to 20, with negative 1. So we can start with the negative value, and we can go to the positive value, and this will specify, let's say, the x dimension, and we can also make one for the y, and let's make it actually a little bit smaller. So we start with maybe 20 by 20 floor, and then for z we're going to do we're not going to actually multiply it with negative value. We're going to start with 0 and then go up. So we can go up. Let's actually make it a cube first, then maybe we can play around with the proportions of this volume. So inside of this, I'm going to create some sample some points and curves. Basically, these are going to be used to define where we want the mesh volumes to populate, right? And that's what Cocoon is going to calculate. So once you load the plugin, you're going to see it under the mesh tab. Cocoon is here. So we can basically place boundary representation charges, curve group charges, and point charges. It's actually pretty straightforward. Once you have some points, you can convert them into point charges for volumetric calculation. So for this box, we can actually do a few things. We can use populate 3D to get a bunch of points populated in it. Because we are doing because we're calculating a volume, we have to be a bit careful with how many points we sample in the beginning, because if you put too many points, sometimes the computation takes a lot of time, and you might want to test for the tolerances for the values using lower numbers. So I would suggest we start with maybe between 10 to 20 numbers that are randomly populated in this volume. So let's say 15 points. And these are the locations for those points. We can also attach a seed. If we are unhappy with the population, we can randomize their location. And I'm going to turn these into point charges. So if you go to Cocoon tool under point charge, we can attach these to be point charges. Now we can supply two values, so the radius value and the strength of charge. So the radius value is basically how much volume they occupy, and the strength of charge basically affects how the computation for the connections are made. So you can actually randomize these. We can actually experiment with this, but you can do, for instance, let's say we want the radius charges to be between 6 and 10, and we can place a random generator here, define this as the domain, and depending on the number of points we are sampling, we can assign a random charge value for these points. So I can attach it like this, and the strength of charge, it could be between 1 to 2, so it doesn't have to be actually too much. We can do let's start with 1. You can also randomize these strengths to affect the calculation of the surface. You can experiment with that. So the point charges are there. The next step is basically calculating, wrapping up the geometry with marching cubes. So what's going to happen is all these points are going to become kind of like volumetric brushes. So they're going to be mesh volumes at the location of the points, and they're going to be turned into a continuous surface. So the marching cubes command takes in charge objects. So these could be point charges or curve charges. I'm going to start with point charges. The target ISO value, it basically affects how the surface is computed. Normally it's supposed to be between 0.2 and 0.3, so you can start with 0.2. And target size for each sample cube, this is basically the sampling size for the marching cube. You can see that I have a 20 by 20 cube, so we can actually feed in just one for this. If you want more resolution, you can make it 0.5, so that your grid definition is a bit more. But all these values you need to actually test out a bit. So the execute algorithm is a Boolean toggle, so I can place a Boolean toggle here. So when I turn this to be true, it is going to compute a mesh for me. So if I make it true, that's the volume that these charges actually output. So the advantage is, because we started with, let's actually turn off the box. So this is the volume of the mesh that I got. So if I bake this, geometry, you can see this is the volume. And if the meshes are not connected, then we get separate elements, right? So the radii, you can see they're varying as well, because I randomized the interval, so we can have different types of volumes. I'm also going to add one more thing to this. I'm going to add some curve charges as well, so to see what it looks like. So we can actually do, let's say we are doing population 3D. Let's actually do something else. Let's keep this here, and we go to the box. So I want to get the top plane and the bottom plane. Let's say we deconstruct the box. You can actually deconstruct the box, or you can do deconstruct brep. So once you deconstruct the brep, you can let's see, you can actually get the faces of the brep, and let's do list item. So this is the left side. Let's actually find the bottom half, or this is the top half. This is fine. So we can also do populate 2D. So the region, it requires a rectangle region, so we can actually get the wireframe of this surface and join these curves into a rectangle and feed this in for the random sampling in 2D. And let's actually get just 5 points, 5 random points. We can also attach a seed here if we want to change the location of those points. So these are the points on the top plane. I'm also going to do something similar for the bottom plane. So let's actually make a copy, put it down, and this one we want the bottom surface, which is here. So it's list item 4, and I want to get different points there. So we can do different points, which are like such. And let's see. So these guys we want to connect. Actually, let me disable this top part so we work on this part only. So we have 2 sets of points, and we can connect them any way we want. We can actually make them connected with lines. So they could be lines like this. We can also make Beziers. So let's make them Beziers. We can actually do, so this will be, this is the bottom point. Then we can do a Z vector with, let's say, a vector direction or strength. And then we want these points to go to the top plane, and we want this vector to be reversed. So we get these sorts of connections that are randomized. So this is actually, these are the curve charges. I only made 5, and I'm actually going to bring the cocoon part here towards the right a bit. So you remember we did point charges. We can also turn these into curve charges. So let's look at how the curve charges work. So I come in here. I'm going to actually get similar parameters, so we can copy the radii and the strength parameters, but the numbers, they have to be 5. So that number is located here for how many points we sampled in the top and bottom plane. And these become the radii. So I have 5 radii values, and these are the charge strengths. Then we can also copy the cocoon calculation here and look at how the curves actually work, right? So these are the curve volumes. So I'm going to bake this too. So these are the curves. So that's kind of the difference. They're actually a bit more thicker than I thought. So let's actually reduce them a bit. So maybe we go from 4 to 6, right? So we get a little bit more thinner elements. So they're a bit like that. So these are the curve charges. These are the point charges. Now let's see if we can actually combine these two. I'm actually going to reduce the charges a bit. So we can do 3 here, make them a bit thinner. This one also, let's make it go from 4 to 6 for point charges. So we can actually merge these two calculations together and see what we come up with. So these are the point charges. This is their volumetric calculation. Let's also check that that's going to be okay. So these are the volumes for the points. They're actually not connecting as much. So maybe we can increase the threshold for the points a bit. So let's make it from 6 to 8. I think that might be okay. Still, one thing though, because the curves and the points, they're actually going to create 2 different sets of geometry. So if we can hide the box, let's see, hide these guys as well. So if I bake this, you're going to recognize that they're actually discontinuous. If you want to make something more continuous, you can see they're actually causing 2 different sets of calculation. So we can go with one or the other. You can also combine these, but if you combine these, you're going to get these sorts of breaks or kinks in the mesh. So maybe that's not something we want. So maybe you want to resort to using only points. I think points might be okay for this exercise. So I'm going to take out the Bezier, and let's actually keep rolling with the points. I'm going to keep it at 6 and 8, but let's actually make it a bit more now. Let's make this 10. And let's increase the point count. So let's make it 15. There you go. So we have a volume like this. And the next thing I want to do is actually split this using the box. So the box is here, and I want to turn the box into a mesh as well. A mesh is made out of vertices and faces, and we can split meshes with meshes. So we can do a mesh split here. So I want to split the volume that we've created with the mesh of the box, and this will give me two results. It's actually doing two separate forms, but we can do a dispatch and look at the meshes in A, which are the outer meshes, and these are the inner meshes. So if I turn these off, you can see this is the surface I got. Now we have some small chunks that are sticking out, and to fix that you can either play around with the random seed or change the number of points. You can just simply change the seed and we get a new mesh. So let's check how this form works. So I'm going to bake it. This is its form actually. It's a bit thin here. We can maybe randomize it again, but this is kind of the form I got. Maybe we can increase the sizes a bit more. So let's say we do 6 to 10. We can maybe increase that a bit more. Let's see, or decrease maybe. So let's decrease the number of points. The connection here is missing. So you have to experiment with kind of the output a lot, but you can also test the interval. This is actually fine. I want to first show you the workflow, which is we split the mesh so that we get kind of the inner hollow parts. Then what I want to do is get the floor slabs placed and split the floor slabs with this mesh. So to do that, we go back to the box, the dimensions for the box. So I want to create a series of planes in the vertical direction. So those planes are going to be XY planes. And I want to create a series here. So the series are going to be connected to a point, XYZ point. So these are going to be the Z values. And we can define some sort of interval. Let's say we want floors that are on every fourth level. So we can do, this is the step size, and for the total count, we can put a manual number there, or we can divide this value with 4. That could actually make it a bit more precise, because this is the total height and this will give us 5. So these are the points. I'm actually missing one on top, so maybe we do divide, and we could do addition, and we can add 1. You can also write an expression here, which will also make it work. So these are the planes, and I'm going to bring the plane here all the way here, and what I want to do is calculate the section of the plane. Actually, we want to calculate the section of it with the box, with the mesh box. So you can do mesh plane intersection, solve intersection events for a mesh and a plane. So this is the mesh for the box, and these are the planes. So we get these surfaces, these planes, and then we want to do boundary surface, because these are curves, and then we want to mesh these as well. So now they're all meshed out. Now this is the tricky part. Let's see if it's going to work. So basically we have a mesh here, and we have these floor slabs. So what I want to do is do another mesh split. I want to split these floor slabs, so you need to flatten it out with these surfaces. So I do flatten that as well, and we should get 2 sets of meshes. So if I do dispatch here again, we would get 2 sets of meshes. So you can use the inner ones or the outer ones depending on how you want to use them. So these are the it's giving me some invalid geometry, because I think there are nested geometries in there, or this is actually not working well. Let's see, maybe we can move around the point sampling a bit. So these are the meshes. Let's look at this one. Maybe this came out a bit better. Yeah, this came out actually a bit better. The ones that are inside. The guy at the bottom, I think it's slightly not working, because this guy at the bottom, it's somehow tangential to the volume. So the ones on top and the bottom, they're kind of tricky, but the ones in the middle, they seem to give you the right division or the surfaces. You can also bake both of these and trim them or clean them out, depending on how you want to work with that. But essentially, this is the workflow. So we first trim the inner mesh, the volumetric mesh with the box, and then that trimmed version we can use it to trim the slabs as well. Another way to do it might be to actually maybe not do the boundary with the box, but do it with the volume. So I haven't tried that one actually, but let's try. So you remember, this is our volume. What if we calculate the intersection with this boundary instead? So let's try that actually. So we calculate this boundary, we get these curves. Let's see. So these are the sections, and it doesn't actually calculate it very well. So maybe go back to the older version. So that's it. And let's go back and let's see. Let's play around with the parameters a bit. So I'm going to disconnect this part and disconnect this part. Then what I want to do is look at the initial box, make it a bit more like vertical. So increase the height, maybe make it like 50. Then let's look at our population before the point charges. So these are where the points are going to be sampled. And we can increase the number a bit now. So we can make it maybe 30. So these are the volumetric charges. Maybe increase the charge interval a bit. And let's first check that our surface is working well. So I'm going to disable the mesh split. Let's enable the point charge. This might take some time because we're increasing the number of points as well. But I got a mesh volume that looks like this. So that looks actually good because it's also continuous, which is something we want. So we got a shape, a volumetric shape like this. Then you can also play with these ISO values. ISO value would actually could shrink or enlarge, and as I said, the cell size controls the resolution for your mesh. One thing we could also do is refine this mesh, so something that is located here. So you can also refine the mesh that we get here. So this is the refinement mesh, and there are some values that you need to enter here. So I'm going to check my notes. I haven't memorized them, but basically for the samples and the valence passes, you want to give a value that it basically does these two values are iteratively done, so it kind of iterates through the mesh to fix some values. Sampling increment, let's see, sampling increment, we can actually do, let's see, refine the output from Cocoon. Number of Laplacian smoothing, we can also do 12 for that. Sample tolerance is 0.01. Let's do 0.01. Sample tolerance. Laplacian smoothing is 10. Number of times to subdivide, you can keep it at 1. If you add more triangles, it might actually take more time to compute. And let's try, we need also one value for sampling increment. Let's actually leave it as 1 as well. Let's see. It doesn't work. Let's see, sampling increment. I checked my notes, but this actually should be okay. Let's give this sampling increment some other value, maybe 0.01. This is the mesh. Let's see, 0.5. Oh, the refinement data. We need to get the refinement data. Yeah, my mistake. So you need to actually connect not the mesh but the refinement data here, because it needs to look at the topology, not the geometry, to find the computation, to do the right computation. So this is actually refined mesh. Now we can input this guy here and see what we get. So I'm going to turn these off for now, and let's see, this is the splitted mesh. You can actually barely see it in there, so let's disable the box. So this is the geometry that I got. There is a bit of this kind of surface sticking out over there, so maybe we can try another random seed to get kind of a nicer trimmed mesh version, mesh volume. This seems okay. There's a small part over there. Maybe we can increase the volume. This is actually too much now. Let's decrease it. So you can do these sorts of iterative passes. You can also delete these probably, but that seems okay to me. There are some like tiny areas. Let's try 12. And maybe another random seed. I can also increase the point count, actually. I think that's okay for now. Let's keep that. And this is the mesh. Let's bring in the planes. The planes are here, so we need to enable the points so that we get the planes. Boundary meshes, these are the surfaces, and these are the inner slabs. So that was the workflow I described. Now let's actually bake some of these and see what we come up with. So we bake the surface, and these are the mesh slabs. So this is kind of the geometry output. So you need to actually like try maybe other versions. I'm actually going to do the other slabs as well. So let's try the external ones. I think the external ones might be a bit better actually. So these are the two versions of this volume. We are actually not left with too much slab area here. The volume is too big. So maybe we can go back and reduce the meshes. This is actually this version is a bit better. So it's like checking the inner geometries. Let's see. So maybe we do reduce the number of points a bit. Yeah, so that seems okay, I guess. So let's try that one actually. This guy is the surface, and these guys are the slabs. So let's see how that looks like. Okay, so that's basically actually it is giving me kind of the irregular surfaces as well. So because I did a regular dispatch, the issue is some of the slabs are not coming in from the right surfaces. I realize that now. So if I bake this, you might have to go in and clean it up, and there may not be an easier version of testing this out. Basically, if you want to keep the inner surface, you need to manually delete it or clean it up probably. You can also play around with the volume, but essentially this is kind of the geometry output for the Cocoon. So you can work with the curves, with the points. I try to do one or the other, because if you try to connect them, then the mesh refinement kind of shows like sharp transitions. This is actually, it works better if the geometry input is similar. So in that sense, you can use points and curves and try to get kind of a nice smooth surface, and then do something with that. So you can actually intersect it with other meshes or planes, and define slabs or other types of surfaces in it too. Okay, so I hope this was helpful as an introduction to Cocoon, and if you have any questions, you can leave a comment below, and there are also other resources on this channel, so I would like it if you subscribe to the channel to support it, and thanks for watching.